So at the end of the last class, we we were looking at these hydrocarbon derivatives, this idea of functional groups. And within the functional groups, there lie a handful of different functional groups that have a similar component to them, and that's these four, right? Aldehydes, ketones, carboxylic acids, and esters. And within those four, we have, and we'll go through all of the functional groups except for halohydrocarbons, which we already did. We'll look at the alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, and amines for nomenclature today. Before we get to that, I really want to stress this idea of a carbonyl. Okay, so a carbonyl is this component. So you can say, here's my little squiggly line saying there's something bonded to a carbon. And you have a double bond of that carbon to an oxygen, which the oxygen has lone pairs of electrons, to another thing, okay? And so this carbonyl is part of those four functional groups for a reason. And this is where, you know, the secret to chemistry really comes in, is this: if you're going into organic chemistry, understanding the carbonyl group is going to be of utmost importance for understanding the reaction chemistry that you're going to do. A lot of the difference between organic chemistry and general chemistry is sort of the structure. You're going to learn a lot about a bunch of different chemical reactions that occur between these functional groups. And if you take the approach of, I'm just going to memorize what the reactants are and what are the solvents and all that stuff, you're going to have a lot of memorizing to do. If, however, you understand the carbonyl group, you'll notice that a good portion of the chemistry that takes place in an organic chemistry reaction takes place because of the secret to chemistry that we talk about, you know, in my Chem 101 and 102 classes all the time. The whole idea of charges, right? That's the whole idea, secret to chemistry, charges. And in particular, we can actually narrow it down to this other thing, this electronegativities, right? The electronegativities are based on where do the electrons go? Where do they exist within a bond? Are they on one atom versus another? And the carbonyl group is a really good example of this, because if you take, and I'm going to just draw it a little bit bigger, if you take that carbonyl, carbon and oxygen bond, there's a big key here, right? If we look at the electronegativity difference between these two atoms, right? The delta En, from way back in 101, right, will equal the electronegativity of oxygen minus the electronegativity of carbon. And so that's going to equal 3.44 minus 2.55. And so you get a value of 0.889. Okay? And so this bond is polar. Okay? It's polar. It'll have a partial negative on the oxygen, and it'll have a partial positive on the carbon. And that's going to be what governs a lot of the reactivity in organic chemistry, is because there are going to be two types of substances that are going to interact with these carbon and oxygen, with these atoms. One of those substances is what's called a nucleophile. Right? And the name says, right, loving of a nucleus, right? Something that wants a positive charge. Right? So a nucleophile is going to be largely a base. Okay? And so for a nucleophile, you might say something like ammonia would be a nucleophile that you could look at. Something that has, so something like NH3 that has this lone pair of electrons. It's usually, so it's this Lewis base in particular. So what happens here is that nitrogen has on it a partial negative, and it has this lone pair of electrons, and that lone pair of electrons will preferentially react with that carbon, right? Because the negatively charged nitrogen with its lone pair will be more likely to interact with the carbon that has this positive charge. And that's going to start off a chain of movement of electrons within this part of a functional group that will lead to bonds being formed and bonds being broken. Okay. The other thing that you'll find is what's called an electrophile. Right, and an electrophile, something like you might say an H plus, right, or where that H plus will preferentially hit the side of this carbonyl that has the oxygen on it, because that oxygen has the negative charge. If you start to go into organic chemistry with this in mind, with the idea that electronegativity is going to govern how reactions begin and how they cause reactants to have bonds formed and broken, you'll wind up with an easier time in your organic chemistry class, right? It's all about charges. What charges are attracted to what charges? Well, we know opposite charges attract. And if you look at this carbonyl molecule as being something that has a partial negative and a partial positive, that's sort of the first step of sort of getting your foot in the door for an understanding of how a reaction begins. Once you see how a reaction begins and why a nucleophile will, and using the terminology that you'd use in an organic chemistry class, why that nucleophile would attack that carbonyl carbon, right? If you know that start to it, then you can sort of trace what's called the reaction mechanism a little bit easier. And the reaction mechanism in an organic chemistry class is really seeing not just what reactants there are for steps like we did, you know, in the kinetics section. It's actually looking at where do those electrons go in a stepwise manner to get you to a product. Okay, so that's the first thing, and that's why I wanted to spend a little extra time on this, because it wasn't, you know, I loved my organic professor back in college, but it took a friend of mine in grad school who was an organic chemist who really helped me to understand it better. My particular professor didn't always wasn't always as good at communicating some simple concepts as that. And so if you can look at it from the simplest standpoint, everything that we do in chemistry is based on charges, then in this case, you'll start to be able to approach organic chemistry in a much more accessible way, and hopefully do a lot better in organic chemistry than I did. So with that in mind, you know, you're getting that intro to organic chemistry, and the next thing, the tedious part of that introduction to organic chemistry, is the nomenclature, right? We want to have that introduction to nomenclature so it's a little bit less memorization that you have to do when you get into the organic chemistry class. And so nomenclature for alcohols. Remember, we're going to talk about an alcohol has a general structure, R, which is just a hydrocarbon bonded to an OH. And remember, this is a covalent bonded OH. And so when we do the nomenclature of an alcohol, okay, we're going to change the ending to OL, okay? So if you were to have something like this, right? You have essentially an ethane and you have an alcohol, okay? And so what you'll do is you'll knock off the E and you'll change the ending to an OL, okay? And so this becomes ethanol, okay? If you have propanol, so ethanol is a really simple one, right? Or you could have methanol if you have it just to a CH3, but you could also have propanol. Well, there are a couple versions of propanol. You have the first version, which has the alcohol attached to the last carbon, okay? This is considered to be a primary alcohol, okay? Right, it's bonded to the last carbon on the chain, or the end carbon. Right, and so on this one, again, we would do this where we would number the carbons based on where the substituent is. So it'd be 1, 2, 3 in this case. So this would be 1 propanol, or propan 1 all. And this is sort of the second way of writing. I believe that's the actual IUPAC way officially, although 1-propanol is close enough and it's common enough to use that. But the propan-1-ol is particularly useful if you have other substituents on that particular molecule. Okay. The other version, which is a secondary alcohol, okay, is where it's bonded not to an end carbon, but in this case, the middle carbon. So we'll have a CH3, here, let me try this again. I'll just draw out the whole Lewis structure of this. So you have your CH3 bonded to a carbon, well, maybe not the whole Lewis structure, bonded to your alcohol, bonded to CH3. So this particular one is what's called isopropanol. Okay, this is a secondary alcohol. In other words, this alcohol is bonded to what's called a secondary carbon. This secondary carbon is bonded to 2 other carbons. So isopropanol is the common name. It's also known as 2-propanol or propan-2-ol. Okay. So that would be the alcohols themselves, right? We're basically numbering them what carbon, right, the alcohol is attached to. We're still using the root, and now we're using the ending of an OL, right? So the root and the ending, okay? If you were to have something like tertiary butyl alcohol, right, for that one, you'd have a carbon in the middle where the alcohol was bonded to a carbon that was bonded to 3 other carbons. So this carbon here is a tertiary alcohol, okay? And so there's the OH bonded to that. And so this one would be tertiary butyl alcohol. Okay, that's so tertiary butyl alcohol or T-butyl alcohol, or tert-butanol or T-butanol, right? To show that that oxygen is bonded to the tertiary carbon, okay? So these are some different ways that you would name alcohols. The key though is just that you're really changing the ending to an OL, and you're using that same root, okay? So, you know, I'm not gonna try to trick you on this, right? Oftentimes you're just gonna wanna identify a functional group, and if you can name it, it'd be a simple alcohol to name. Okay. That's alcohols. Also, things that we have are ethers. So R, O, R prime. So on this one, you basically have 2 alkyl groups on either side of an oxygen. Okay. So 2 alkyl groups on either side of an oxygen. So the most common of these is, and I'm going to start out, I'll draw out the condensed structural formula. So CH3, CH2O, CH2, CH3. And so this one is diethyl ether. Okay, and that's how you're going to call it. What you're going to call it. You're basically naming the alkyl groups. And then you have the word ether on the end. So if you have this, and of course the line angle drawing of that looks like this, and you can put the lone pair of electrons in there. right? This basically gives you the same structure, right? With the line angle. Another way to do it, if you wanted to say have two different alkyl substituents on it, what you would do is, so have your CH3, O, CH2, CH3, you do it alphabetically. So this would be ethyl. So you have your ethyl group there. Methyl, ether, right? And so in this case, your ethyl, methyl ether, right? You're just naming it based on the functional groups, okay? Or if you wanted to say, this one here, right? This would be ethyl isopropyl ether, right? So again, you've got the word ether that you're attaching on to the after you name the alkyl groups. And if you have two alkyl groups, you'll just add the di to it and say, diethyl, for example, or diisopropyl, or dimethyl ether. On this one, you're only going to have two things ever bonded to oxygen, so you only have to take into account those two sides of the oxygen. So there are ethers. Aldehydes, and so aldehydes have this R bonded to a carbonyl carbon, where that carbonyl carbon is bonded to a hydrogen. Now, the simplest of them is one that you really should know, just if nothing else based on trivia, right? Which is, and you may have heard of this, especially if you've ever dealt with biological samples that have been preserved, right? This is formaldehyde. Right, and so that's a common name that we tend to use for that. But there are other names for aldehydes. And so with the aldehydes, we basically have the ending, if you will, of Al. So dash Al. So if you will, I'll go back to propane again as our example. CH3, CH2, CH, excuse me, let me do that again. Actually, I don't need to. There we go. CH, there we go. So this one right here has 3 carbons and it has an aldehyde on it. So the 3 carbons says propane. The aldehyde is going to be on the first carbon, right? The aldehyde says dash Al and it's on the first carbon. Okay. Yeah, so this would be 1 propanal. Okay, knock off the E, add the Al ending. Or if it's on the second carbon, so CH3, C, double bond O, CH3, right, would be 3 carbons long, but it's on the second carbon, right? And so it would be 2 propanal, or propan 2-al. Okay, this one up here could also be called propan 1-al. Okay, so that's propanal. So that's how you name your aldehydes. Basically, you use the Al ending to do that. Okay, so if you see Al, you know it's an aldehyde. You also have ketones. Oh, hold on, I totally messed that up. Excuse me. This is not an aldehyde. Where am I? Where's my head today? Just like it always is in organic chemistry, apparently. Gone. That would not be an aldehyde. Haha. You don't actually have to number these. Wow, I am just screwing my brain up, aren't I? Oi. With the aldehydes, in fact, you don't have to number these. See, this is one of those things that I kind of screw up every so often because nomenclature is my least favorite thing in the world. With propanal, you don't actually have to number it because it's always on the end. Duh. I am ready for this semester to be done. let's go back to our, so it's always on the end. And so it would be, if you were to have something like this, right, you'd have a double bond there, that would be butanal. And you know it's always on the end because it's this carbon here is bonded to the H, right? Ugh. Okay, propanone is the actual one that would have been what I was doing there, which I'm an idiot for. Tells you how tired I'm sure we all are at this point. So this one is a ketone. And so the ketone, the difference between an aldehyde and a ketone is that you have an R group, carbonyl, and some kind of an R group, R prime. That R prime can equal the R, so it's a hydrocarbon of some kind on either side. So this would be propanone, because the ending is going to be O-N-E. So this would be propanone. With propanone, you don't need to specify it would be on the second carbon, because if it's not on the second carbon for propanone, it would be a propanal. However, if you were to have something like this, this would be a pentanone, but you have to specify, so 1, 2, 3, 4, 5, or, and that the reason you have to specify that is because the O can be on a different carbon. How to wake myself up there. So this would be 3-pentanone, or pentan-3-one. Oop, pentan 3-one, or this would be 1, 2, 3, 4, 5. Would be 2-pentanone, or pentan 2-one. All right. Whew. Where is my head today? All right. Next.
Professor?
Yeah.
Sorry.
Yeah.
Quick question. So only if it's not on the ending, then it's
right.
an own. Okay.
Yeah, yeah. It's an aldehyde if it's on the end, and if it's not on the end, it's a ketone.
Okay. Thank you.
Don't know where my head was a minute ago, but it's back. Okay. Carboxylic acids. Okay, so carboxylic acids now, they're going to have this R bonded to C, double bond O, so your carbonyl bonded to an OH. Okay, so with a carboxylic acid, you've got, again, so what we're doing here is we're going to change the ending to an OIC and the word acid. Okay, so if you wanted to look at our good friend acetic acid, all right, so acetic acid, which is CH3COOH, right? We can write it out like that, or right, like this. This should actually be considered, well, there's 2 carbons here, so it's an ethanoic acid. Right, so the 2 carbons says ethan, right, and then you've got the oic acid. And so you could have CH3, CH2, C double bond O, OH, which would be propanoic acid. Okay, and so again, you're taking this 3-carbon chain, right? That's your propan, and then your oic acid. Okay, so that's your carboxylic acids naming. Okay, now the next thing on the list is esters. Esters have, oop, totally, there we go. So I'll do that up here. R, C double bond O, your carbonyl bonded to an O, bonded to some other hydrocarbon, okay? So on this one, what your naming is coming from is the type of chemical reaction that leads to the formation of an ester, right? So esters are formed through a dehydration reaction. Okay, a dehydration reaction, right, is loss of water. So you could form you can form an ester through a reaction that's similar to, or basically showing, I can show you one reaction that'll do that right here. CH3, CH2, C, double bond O, bonded to OH. Okay. Now this particular type of reaction, so what you have, right, this is propanoate, or excuse me, propanoic acid. And the way you form an ester is that carboxylic acid will react with an alcohol. Right, this is methanol. And what winds up happening is, to form this particular acid, this dehydration reaction occurs whereby you lose water, and the water actually comes from the loss of the OH off of the carboxylic acid, and the hydrogen, that terminal proton on the alcohol, leading to the formation of an ester. And the ester would be CH3, CH2, C double bond O bonded to O, CH3 in this case. Okay, so that would be your structure there. And the way this works is you would take the carboxylic acid and you'd get rid of the oic acid, and you'd change that to, say, propanoate. Right, so this would be now propanoate, okay? And then you'd go over here to this other piece and say, oh, well, that methanol is coming from a methyl. And you'd put these two things together to form the name of it, which would be methyl propanoate. Okay, so it'd be methyl propanoate. Okay, and so basically you're taking the name of the root for the alcohol and the root for the carboxylic acid, you're putting those together and changing the ending to an OATE. And the rule for which one comes second is really based on which one came from the carboxylic acid, right? That goes second. And the one that comes from the alcohol, right, goes first, right? And so that's how you get esters, this dehydration reaction. And again, that dehydration reaction is going to occur in such a way that the reason that you lose the OH from the carboxylic acid has to do with the what we talked about with carbonyl groups before, where that carbonyl carbon has a very even more positive partial positive on it than the methyl oxygen. Excuse me, the carbon bonded to the oxygen on methyl. Finally, we have amines. And so for amines, it's actually going to be really simple. You're going to say you have the IUPAC naming would be amino, and then the root alkane. Okay. So if you have something like CH3CH2 NH2, this particular one will be, well, you have an ethane and you have an amine, right? So as a reminder, this is R bonded to an NH2. So this would be amino ethane, okay? And so that's really as simple as that, right? We're just taking the root or the alkane name, and we're adding amino to it. We're changing, instead of amine, it's an amine O, so you drop the E, it becomes an O, and then you take the root of the name of the alkyl, or alkane, excuse me. Okay, so there's our nomenclature stuff. A little tedious stuff, but it's important, and seeing it now hopefully makes it a little easier to see later on, right, when you go on to organic. All right, so there's our nomenclature, and that finally brings us into talking about some interesting molecules in organic chemistry. Okay, so polymers. Polymers are organic molecules that are large chain-like molecules built from smaller molecules called monomers. So when we talk about a monomer, monomers are going to be really tiny things, and you link a bunch of them together, and you link them together through chemical reactivity, oftentimes using a catalyst, right? So there's polymer or polymerization catalysts. Now, we're not going to get into the mechanisms of how these reactions work. Suffice to say that there are different types of polymers out there, many different types. We're going to look at a few of them. One of the ones we're going to look at is the addition polymers. Okay, so addition polymers, essentially you have these small molecules that add on one after another to form these really long chains. We'll also look at some condensation polymers. So condensation polymers happen through dehydration reactions, as you might expect, something to do with water, right? And so the first of this bunch that we're going to look at is called polyethylene. Now, what we'll write out first is the monomer, easy for me to say, the monomer for each of these three polymers. Each time we'll write out the monomer, and we'll see what it's going to make. So with polyethylene, what you would have is essentially in some number of ethylenes, right? So C, double bond, C, onto an H, onto an H, onto an H. So this ethylene's a gas, so this is a gas phase reaction. So you pump in a gas into the presence of a catalyst, and it'll start to form polyethylene. This is something that you see on things like plastic bags, lots of different plastics out there, plastic water bottles and the like, really hugely produced industrially. And you basically add a catalyst to it. And what happens is you make a polymer that is, and this is sort of how we draw out the polymers from here on out, but you take these double bonds and you open up this double bond and form, so basically what happens is this carbon will take one of the electrons from the double bond to form a bond with the next carbon and of another ethylene, which will take and form another bond with the next carbon of the ethylene, etc. And so you make this structure where each of these monomers within the polymer chain is just basically opened up its double bond to form single bond. So it makes an alkane from an alkene, right? And so you have some number of these, right? So in, -1, if you will, and you've got carbons and hydrogens, etc., right? So you've got these ethylene molecules or ethene molecules, which polymerize to form a set of linked ethane molecules, essentially, right? So this long now carbon chain of these, and this is called polyethylene. Another common one out there is Teflon, and Teflon is trifluoroethylene. So instead of having carbons that are bonded to hydrogens, now they're all bonded to fluorines. And the reason that this is so useful is because having those fluorines, the fluorines themselves, they're really electronegative, they're small atoms, they don't want to interact with much when they're part of this molecule. But if you add a catalyst to it, you can make the polymer Teflon, which is the same basic structure as the polyethylene, except now your carbons are all bonded to fluorines. And since those fluorines are nice, we actually have a term for them. They're really small, they're really electronegative. We say that they're hard atoms. right? So you make this long chain of these tetrafluoroethylene molecules, so it becomes what's called Teflon. Another of the addition polymers that are out there, again, notice these addition polymers are often and largely based on the ethylene, right, or ethane, okay, molecule. So if this is ethylene, this is tetrafluoroethylene. But they often have, or usually have, this C double bond C, right? This ethylene structure to them. So polystyrene is no different. Well, it is a little different in that it has other things bonded to the carbons. So this is essentially an ethylene with a phenyl group. Okay, so this particular molecule, again, you take that with a catalyst, and this molecule will form long polymer chains also, where you have carbons all bonded in a row, and coming off there, you have a lot of hydrogens off there, but every other one of these has a phenyl group. Okay, and polystyrene and Teflon and polyethylene, they have very small changes to their structures overall, but for the monomers, but they have huge changes to things like their interactions with the molecules that would otherwise stick to them. For the case of Teflon, polystyrene tends to weather heat or be more resistant to heat than polyethylene is, which is why a lot of polyethylenes, you don't want to push them and put them in the dishwasher, right? If you put them in the dishwasher, they heat up and they will often deform or melt. Polystyrenes often don't do that because they're more heat resistant. But also part of these polymers, right, they don't just form a polymer from the making of these long carbon chains, or rather, they form the polymer because of the carbon chains, but they don't form plastics because of the carbon chains. There's also some other aspects to making plastics, and with what are called plasticizers to help link those chains together. But in general, the plastics that we think of as polyethylene or Teflon or polystyrene, they are mostly based on their properties are based on the structure of these monomers, which come together to form the polymers. Okay. So another type of polymer is a condensation polymer, and nylon is one of those. So see if I can draw this out well. That's a challenge here. So here is a nylon polymer, and what are going to come together to form this H2N. So it's an amine with CH2 repeating. There's 6 of those in a row on either side of this. So basically you have a 1,6-diamino methane. So on the other side, you have that and that. With this particular molecule, that's going to react with a dicarboxylic acid. Okay, so these are the molecules that condense, right? So when we say they condense, right, we have a polymer that's formed when water is lost, and the water that's lost is similar, so it's similar to the ester reaction, but instead of an alcohol, you have an amine, right? You lose the water molecule there. Try this again. There we go. And you make this polymer. And this reaction can be repeated because these two molecules have the same functional groups on either side. That's why you can make these long chains. Hold on, that's not an N, that should be a 6. And that should be a, oop, left my 4 out there. 4 there. C double bond O, bonded to OH, right? And you could do this again. Right, you could do this many, many times over. That's the whole idea there. But this is the condensation reaction where basically you produce water in the making of something like nylon. Proteins are also examples of condensation polymers. Proteins just happen to be biological or natural polymers, and so proteins. For a protein, we can look at something like an amino acid. I'll try that again. There's a little bit more space here. Okay. So with our amino acids, so an amino acid is going to have a functional group here. We'll talk a little bit more about those in a little bit. N H lone pair. So you've got your carboxylic acid on the amino acid and your amine on the amino acid. Again, we'll talk about what this R group is a little bit later and the functionality of that. But that will react with a neighboring amino acid to form a bond through to these two molecules through a condensation reaction. Okay, where the condensation occurs between the OH from the carboxylic acid, right, and the hydrogen from the amine, right, to form, at least in this case, what's having trouble, right, there we go, that's better. Write this more upright. There we go. To form a bond between those two amino acids. Oop, there should be an R and an R prime. Come on. Okay. And so that's how your, and then plus water as well, right? And so that's how your proteins are formed through the condensation of amino acids to form polymers. Okay, now something about and I'm missing, I didn't write them in here, I probably should have, so I'll do it right now. So the amino acids are all fall into a category of what are called chiral molecules, and chiral molecules have a handedness to them. Okay, essentially, the idea of chirality is basically the property of handedness. Okay, when you think of your left and right hands, right, they're not superimposed, or they're mirror images of each other, right? They look the same except they're just, they're mirror images. They're not superimposable. They're not the exact same thing. They're just mirror images. And you can see the similarities, but they're sort of the opposite configuration of each other, right? Now, when you have molecules that you have a central atom that's bonded to 4 surrounding atoms in a tetrahedral structure, for example, this is one way you can have that. And all 4 of those surrounding atoms are different. They have chirality, they're chiral molecules. And so when you have amino acids, and so that's one we'll look at since we've talked about that already, right? Amino acids have this carbon bonded to a functional group, this R, again, more on those later. They're bonded to an amine, a carboxylic acid, and if you will, it's not pictured here, but going backwards would be a hydrogen back there. And that gives those molecules this handedness. And the nature of chiral molecules is, there's a couple things. One, when you shine light through chiral solution that has a chiral molecule in it, and that light is plane polarized, so all of the waves of that light are oriented in the same direction, the chiral, if it's only one type of, and when I say one type, I mean left-handed or right-handed, it'll tend to rotate the light in one direction or another, so that all of the light that comes through that solution will be still plane polarized, but in at a different angle than it was before. Now, this also has implications for reactivity of these molecules with a variety of different compounds, okay? And so, for example, how does it fit into the pocket of an enzyme or the like, right? Chiral molecules, it'll matter which handedness they have, okay? And so these are called optical isomers because of the nature of how they interact with light. Okay. And so a good example of this, which is sort of coming into the forefront of our understanding, or our need to understand science right now, is sort of, and it's really important to have the right, the correct chirality for a variety of molecules. For example, most of the pretty much all of the amino acids, they're all L amino acids. They all have the same handedness, because you can have L or R amino acids. They have the same handedness. Well, it turns out that historically speaking, this is really important for pharmaceuticals. So back in the 60s, 50s and 60s, 70s, there was a drug called thalidomide. And thalidomide is sort of, the history of this is sort of coming to the forefront of our society right now because of the nature of where we're at and trying to find treatments for COVID-19. People want to use drugs to treat it. And the hope is that you can have a drug that is a safe drug that you can give to people to help treat it, treat this disease, where it'll cure or help the symptoms, but it won't cause other problems. Well, thalidomide was a drug for a variety of conditions. One of them, most importantly, was leprosy. Well, it was also used as a sedative for a lot of people because of other effects that it had beyond just the leprosy treatment. And eventually, because of its anti-nausea properties, it was actually used for a lot of people in pregnancy who were having morning sickness. And so it was prescribed as a treatment for morning sickness. And it was sort of like just the broad coverall. Hey, this helps for everything. Well, at some point after this had been used to treat pregnancy nausea, fetuses were being born with malformation of limbs called phocomelia. And so it was linked to this and people who had this drug. And it turns out that one version of this drug causes these defects, and the other version doesn't. Well, one of the issues with this is the drug, as it was prescribed, had a mixture of both of these isomers, both of these chiral isomers. And so one of the chiral isomers caused the malformation of limbs, the other one didn't. The problem with this is you couldn't just separate them out because and give one or the other, because sometimes in some molecules, they do what's called a racemization, easy for me to say. they become what's known as a racemic mixture, which over the course of time, they will flip-handedness, so to speak. And so when they flip-handedness, you eventually get a mixture of both of these isomers, okay? And so this drug has sort of been, it continues to be called back to the forefront of our knowledge in instances where we're trying to find cures for things because we do not want to be hasty. And this is why we test over and over in as much as we can all these different drugs. That's why we have all these clinical trials, to make sure we don't have similar problems to what happened with all of these pregnant women who were taking this as a nausea medication. And it turns out that the taking of this medication was really important early on in pregnancies, and later on didn't have that same effect. But overall, babies were born with terrible malformations and often died because of one of the chiral molecules, one of these two chiral molecules, which tended to be in a mixture in this drug, thalidomide. So there are also some natural polymers that occur, things that occur from, for example, amino acids, like proteins that form, right? So on the proteins, you'll probably see this if you go on to any type of a biochemistry or some biology classes. So when we look at an amino acid, we have an amine and a carboxylic acid and a hydrogen on all of them. And then there's this other thing, this R group. And now the simplest amino acid is glycine, where this R group is just a hydrogen. And as they become more complex, they can be a methyl or a CH2OH. Right? You can see the complexity changes such that as these R groups, right, those R groups are functional groups on the amino acid that lend functionality to each of those amino acids. Right? And when those functional groups are ordered in a chain or connected together through those condensation reactions, you get a primary structure of a protein, right? That's just a long chain of those amino acids in the polymer, right? With that polymer, though, based on the functionality, there are different things. So you have hydrophobic functional groups, aromatic functional groups, right? Things that have the benzene motif in it, things that are acidic. And acidic things, acidic functional groups tend to hydrogen bond well, right? These nucleophilic functional groups tend to hydrogen bond well. If you have sulfur, they form disulfide bonds, but that leads to, the functional groups lead to structures, secondary, tertiary, and quaternary structures, whereby the intermolecular forces between either neighboring amino acids or amino acids farther on down the chain lead to these more rigidly structured systems that eventually lead to another functionality that's larger in the grand scheme of things, right? And so that's all coming about from this long chain polymer that now has intermolecular forces interacting up and down the chain to form these secondary, tertiary, and quaternary structures. DNA is another example of that. You probably studied that in a biology class, right? Where you have these primarily four building blocks for DNA, right? Where those building blocks are held together through a couple of different types of bonding, right? You have phosphate bonds in the backbone, but you have these intermolecular forces, namely, mostly and really almost entirely, hydrogen bonding between the oxygens and hydrogens, or nitrogen and hydrogens, et cetera, throughout the DNA backbone. And again, leading to that double helix with some other things like pi stacking interactions as well. Okay. And finally, you have a variety of sugars out there, carbohydrates out there that are chiral molecules as well, based on where the the number of chiral carbons and their organization within the molecule. I'm not going to spend any more time on that, just for the sake of we really don't have the time for it. All right, and that takes us to the end. Okay, so with that in mind, we are done with chapter 22 there. I know we went a little bit fast on some things today. I wanted to kind of get to an end of it. There's a lot of applications of the stuff that you'll see more and more in an organic chemistry class. It's not my specialty, so I'm going to focus a little less on some of that. And I'm hoping we'll have some more fun with the transition metal chemistry that will start up tomorrow. Okay, but that's all we have for today. You are free to go today.